This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, I think there's also quiet now, so that's perfect. We start the second session of the morning today with a keynote from Professor Eisert from the Free University of Berlin. Thank you.
Okay, so a warm welcome back. Thanks so very much for the kind invitation. It's a great pleasure and honor, in fact, to give this talk at this wonderful conference that explores the intersection between machine learning on the one hand and quantum computing on the other. And unsurprisingly, this is precisely what this talk will be about. When we have a look at where the field stands and Quo Vadis, where it might be going. So last night I actually submitted the set of slides to our group Slack and asked for feedback and recommendations. And one of our PhD students, it's actually here, said, "Jens, that's a great set of slides, but the title page, is that meant to be kitsch or trash?" You judge for yourself. And to add insult to injury, there's not a single meme in this talk. On a positive note, I will be trying to be as clear as I can. So, one of the reasons we're here today is that while quantum computing has been a hugely stimulating, but at the same time also purely conceptual idea for a very long time, this idea seems to be moving closer and closer to reality, creating a lot of interest in the field, mostly for good reasons, I'm tempted to say. This is largely due to the fact that protagonists, a lot from the US tech industry, but also by some European players in Australia, in Asia, actually setting out to build such devices to a reasonable scale. The machines we have today are still somewhat noisy, yes, and they're far cry from a full Shor-class fault-tolerant quantum computer, even though there has been quite substantial progress along these lines just recently, or just as I'm speaking, but still they're not the full thing yet. But of course, now the question is, great, but what do we do with them? Right? So that's the make or break question. The elephant in the room is whether we can reasonably hope for realistic quantum devices as we have them soon, or presumably soon, to provide some speed up over classical computers. Now, for very much paradigmatic problems, that seems to be the case, or at least there's good evidence that this is the case. And the most paradigmatic of all quantum problems is where you go into the lab. That was a joke, never let a theorist into the lab. And take raw data, and following the Born rule, you would do a sampling experiment taking these raw data. There's some sampling experiments of this type that are so subtle and have so funny tails in the distribution that you cannot sample from a similar distribution classically, efficiently, or sampling up to a constant error in the total variation distance is classically hard, but you can perfectly well do this quantumly. This is a highly exciting setting in many ways. It sharpens the mind of what a quantum advantage is. It's also a bit subtle in that there's no classical verification. You cannot verify these prescriptions based on classical data alone. There's fundamental obstructions, in fact. Whereas you can quantum verify some of these schemes, which is kind of cute. When you think about this, somebody else goes into a lab and takes data, and from these data, you can really infer whether you've done the right thing. You can kind of certify the trace distance or the one norm closeness of the distribution. And then you say, great, but what is it? And then you have to go into the lab. You can certify the correctness of the outcome, but you cannot classically make efficient predictions of what the samples might be, which is a kind of cute thing when you think about this. Again, this is conceptually interesting. It's sharpening the mind, and I think that's good for us. But that can only be a stepping stone, right? So when we say, can we reasonably hope for a realistic quantum device to provide a speed up, we usually think of practically minded applications, or at least one level down applications that have a practical feel to them in one way or the other. Say, when we think of machine learning tasks, those of combinatorial optimization or quantum simulation in a way. This being QTML, the conference on the intersection of machine learning and quantum computing. Obviously, we will take machine learning and put it into the center of things. It's very hard to deny that machine learning has changed the world. ChatGPT is everywhere. The last time I used ChatGPT for a calculation was this morning, with actually hilarious outcomes. Ask me about this. And given the ubiquitousness of machine learning on the one hand, and the fact that quantum computing seems to be helping for certain highly structured problems, the question is on the desk whether quantum computers can assist in meaningful machine learning tasks. Now, obviously, that's the core question of QTML, and that will also be the question that will keep us busy for the next 40 minutes or 35 minutes or so. So there's good news and bad news I have to offer. So starting from this, and I will actually pick up a theme that Christian has nicely presented before, we look at the good stuff, like on steps towards showing quantum advantages or some modest steps in this direction for meaningful and well-defined machine learning tasks, and a bit beyond also, as you will see. That's the good stuff. Next, we will look at the dark side of things, the bad, on what limitations we find in the noise-free setting, but also in the noisy setting, as noise is our biggest enemy. As we know, we have to do something about this, and we see what this means for notions of quantum machine learning. And then, depending on how it goes with time, there will be some phase of meditating a bit of what we have achieved or not, where we have the showdown of the good, the bad, and the ugly, and we come to a nasty shooting. We will see who survives, and we will also meditate a bit what the perspectives might be or might not be, and then we all come together and see where this goes. That's the plan for the rest of the talk. Good. Yeah, indeed, good. Attempts to look at quantum advantages in machine learning. So the perfect world, we would like to have rigorous guarantees for state-of-the-art learning algorithms that are applied to practical, real-world data sets. So you take pictures of handwritten numbers, of cats and dogs. You apply an algorithm, say, stochastic gradient descent, and you apply to a model, say, a parameterized quantum circuit that we love and cherish. And in one way or the other, you want the quantum machine to do better than the classical machine. This can mean many things. It can be that you need fewer pictures of cats and dogs, or handwritten numbers. That would be an advantage in sample complexity, and Sergey in this wonderful talk just before was also alluding to this. It could be faster. That would be an advantage in computational complexity, and you could be doing better in generalizations for unseen data. Now, these are all possible notions of achieving a quantum advantage. So along these lines, first, some good news. So all above, there is a quantum advantage in meaningful Pak distribution learning tasks, where the setting is you have a generator that takes seed randomness and spits out samples from a concept class, like from a family of distributions. So it spits out pictures of handwritten numbers, pictures of cats and dogs, and so on. And the task of the learner is to take these samples and think hard and learn what's going on, and specifically in generator modeling would be able to spit out new samples of handwritten numbers with high probability that are close to the original setting that you had. That's generator modeling, but you could also think of density modeling, where you want to kind of learn the distribution itself in a way. So the first good news is that there is, at least in principle, a quantum advantage in this sense. So here's a bit of fine print, but I'm just saying the same thing that I said before, and I'm also picking up what Sergey said earlier, and also what Christian said earlier, and on Pak learning. This is a wonderful place to be in. So here you have an epsilon and delta, and an algorithm which for every d in a distribution class would given access to an oracle, which here is just classical data you can write on a sheet of paper or have in your brain or what, for that matter, that with probability at least 1 minus delta, so probably would produce a generator of a distribution that is nearby, so it's kind of approximately correct. Again, you take pictures of cats and dogs and you spit out pretty much pictures from pretty much dogs with high probability. And here there is, at least in principle, a super polynomial advantage. And the construction that I cite Christian here is like a proof of principle construction where we make use of a kind of polynomial reduction that builds on a hard-to-learn distribution using pseudo-random functions that are built from Goldreich, Goldwasser-Mikhaili trees, where the point is that using a variant of Shor's algorithm, you can walk the tree backwards, but classically, you get a hard-to-learn distribution. That's nice. It shows there's, in principle, a super polynomial advantage for a meaningful and well-defined learning task. We need results of this type. That's the good news. But then it requires a full fault-tolerant quantum computer, of course, and it's also not meant to be practical. It's like for classical, yes, good, but for completely crackpot and artificial data. I'm not claiming that this is for pictures of cats and dogs or so. It's just been there, done that, good, and that works for generator modeling, but we also looked at density modeling afterwards, and that's true in both ways, and that's what head-to-head also with Christian's nice result that he mentioned earlier, just a couple of minutes ago. Good. So in principle, we are there. The field exists. That's already nice to know. But then you say, yeah, but that's not what it is about. You want to think about methods that work for real-life things, like for practical things, for pictures of cats and dogs, for that matter. What can you do about that? And here's also something one can do about things, in that there is an advantage not in quantum learning, but in quantum training, large-scale pruned classical networks by formulating a new variant of an HHL algorithm that's set up for training pruned sparse classical networks. And that has a super polynomial advantage over families of gradient descent methods. This is a short paper, but it has like a 40 pages appendix with all the fine print where we looked into the detail of not requiring QRAM, but the uploading is efficient and all the different little subtleties here, so that you get a meaningful super polynomial advantage, at least over a large class of classical algorithms of a type. That again requires a fault-tolerant quantum computer, yes, but this is really for classical and natural data. We tried this, at least the presumptions or the assumptions of the theorem, whether they would work for the CFAR 100 data set. That's a Canadian standardized machine learning data set, and it worked well there, so that really kind of works for practical data in this way. That's also nice to know. So it works for pictures of cats and dogs. That's actually not from the CFAR 100 data set. That's our own cat, Minchen. I made it a habit of getting up in the morning at 4 o'clock, and then I put up my laptop, I have my coffee on the right-hand side. But then Minchen also gets up, like sits on the laptop, looks very smart, and puts the claw into the coffee. So no animal was harmed, no worries. But because the cat thinks that's how we do it in our family. But you see, it works for pictures of cats and dogs. So that's good. It again requires a fault-tolerant quantum computer. Can you do also something for a near-term machine? Machines as we have them or might have them soon. And again, the answer is yes. There are quantum advantages for shallow quantum circuits in the sense that there's constant depth quantum circuits compared with log-log depth classical circuits, like NC0 type, so bounded fan-in gate classical circuits with a meaningful locality structure in a fair comparison, so that the quantum learner outperforms the classical learner in a meaningful and mathematically well-defined PUC learning setting, which is, again, good to know. I was here, that it says today. I was hoping this to be out now, but given Australia is like funny on the archive timing, it's not out yet, but I think at the end of my talk it will be out. So it's relatively fresh from the press. It is funny, like Sci rate is dominated by Australia, right? You want to be good with the Australians. Never mind. So the core idea is like to devise a Puck learning advantage from an unconditional sampling advantage that's building on the beautiful work by Bene Watts and Parham, who looked at like unconditional sampling advantage that we kind of changed and built upon by looking at a hyperplane learning problem, so modifying the majority mod P function that they introduced and have a proper concept class so that there's something to be learned of a constant depth quantum learner over a slightly longer classical learner. So again, that's nice. So there's near-term advantages that we can do now and build, or presumably even have been built, on data that we can have. But again, this is for classical and artificial data, no pictures of cats and dogs. So you see there where this is going, that we have the holy grail in the center, and we can fulfill different desiderata. You say, I want this, and then I can offer this, but not all at the same time. So the last word hasn't been spoken, but we are coming closer from different directions, it seems fair to say. That's not in the main topic of my talk, but I will still mention this, that there's also, using similar cryptographic tools, we've seen that there's also quantum advantages in certain families of combinatorial optimization, so in integer programming, which is an interesting subject because most of these problems are NP-hard and worst-case complexity, so that means that, of course, classical computers cannot solve all instances in polytime, but that's also true that quantum computers cannot solve all instances in polynomial time either. So that's a field where you see lots of claims and also stuff in the popular press that's misleading, to say it nicely. So it's a good question to even think like in what way one can hope quantum computers to offer an advantage, and we did so by introducing a cute new polynomial reduction using Occam's razor and computational learning theory applied to a formula coloring problem that we then also related to integer programming. Seeing that there's some instances of integer programming that can be well approximated by a quantum computer, while they cannot be well approximated by a classical computer. So the hardness, easiness region is kind of shifted of quantum versus classical. And this is kind of the way in which you can hope to achieve a quantum advantage of a kind. Very good. So the good part comes to an end. There is, in principle, a quantum advantage in meaningful and interesting learning and also some combinatorial optimization problems. There's room for hope. I've said it. It's not the end of the story, but I think it's good when we strive to think of proven results of this type, but I will add a disclaimer at the end of the talk. The bad, limitations already for shallow quantum circuits. So what we saw, it's like very encouraging, but at the same time, for painting a fair picture, we want to see what are the limitations that we find. And some limitations already come up for completely noise-free circuits, where you want to see, can I prove something for the full food chain of a variational quantum circuit where there's a quantum part in the middle and you take data and then you have a classical algorithm around this and you want to kind of see to what extent this performs well. And that's not so easy to capture mathematically for many reasons. I'm happy to say a lot more about this, but we looked at a sub-problem and saying, good, it makes already sense to look at the quantum part as such, as a Born machine, and say, can you actually learn the output distribution of a Born machine of this type? This is a well-defined mathematical question. We spent like 2 years on this question with a manic depressive phase and ups and downs and lots of outcomes, and some of the authors are also here. I see one PhD student here in the first row or second row and so on. And there's a lot to be said. Not for today. Maybe I single out one result that's kind of interesting in that if you look at this, can we learn the output distribution of quantum circuits? It turns out that for Clifford circuits, the easy dudes, so to say, can be efficiently learned in both in the generator and density modeling sense, sample computational efficiently, which is nice to know. Then you say, sure, I mean, it's a Clifford circuit. It's actually not that trivial. But it turns out that Clifford circuit output distributions are uniform over a fine subspace of finite dimensional vector spaces over finite fields, and then you can cook up a kind of Gaussian elimination problem over finite fields. Good. So you can learn the output distribution of Clifford circuits. Now we know that Clifford plus T gives rise to a universal gate set. That's the father, mother, diverse of all universal gate sets in the quantum industry. You want to have, like we have in quantum error correction, you do like transversal Clifford gates and so on. Then you add T gates with fanciful magic state distillation and whatnot. So the T gates are the hard bit and the Cliffords are the simple, the free bit. So beefing up Clifford circuits with T gates makes them universal. So they say, how many T gates do you need to make the learning problem hard? For simulation, we know what comes out. But now I take my Clifford circuit, I take the T gate, here it is, and I place it into the circuit, and it renders learning hard. A single T gate. And this is kind of funny, because of course, both in the weak and in the strong sense, you can of course still simulate the system. You just look at both branches and you sample over it, or you compute the probabilities. That's clearly possible, but you cannot go back. Once you have the distribution, a single T-gate renders learning hard, and the polynomial reduction goes over learning parity with noise, which is also interesting because there's no noise in the model, but it's kind of effective noise by the T-gate, if you want. And also, Alex, who's also sitting here, will also build up on this in his own talk later. So a single T-gate renders learning hard, a statement that remains also true in an average case sense, which is nice to know, also because we need more average case results as a moral statement, I would say. Anyway, this is an example of some obstructions that we found that may hint at the idea that finding practical advantages may be harder than we thought initially, so there might be some work that we need to be doing to get going here. Of course, the true enemy, the one big Voldemort of quantum computing is noise. Yeah, so that's the big enemy we want to fight. Actual circuits are noisy. When you think of your circuit in your dreams, that's not what you're doing. You wish. What you're actually doing is there's the circuit, but you're actually doing something like this, where there's the perfect circuit that's intertwined with noise. So a good way of modeling this is to think of a random circuit of perfect quantum gates where you add noisy channels that incorporate the noise that you have in your device. This would be noise and decoherence. This could be depolarizing noise. That's the simplest of all noise. It just drives you to the maximally mixed state. It's unital noise. But it could also be other noise, like amplitude damping, like non-unital noise that reduces the entropy. It's all there. You name it. But that's what you're doing, and there's little you can do about this. Well, there is stuff you can do about this. For example, you can do quantum error correction or fault tolerance. It's a wonderful idea, and there's been amazing progress in recent, I was saying years, but actually months along these lines, which is very encouraging. But to be fair, a full fault tolerant quantum computer is still a long way from today. I think few people will disagree with me in this. So then you say, okay, but how can we undo noise in a largely classical fashion? And that's a beautiful idea. This goes under quantum error mitigation, or it's like a family of protocols, not one, but several. Here's one that accepts that adding noise to a quantum system is much easier than subtracting it. Messing up things is usually not so difficult. Hate to break it. And then you add different noise levels to your system, and then you take data when you want to estimate expectation values, and then you extrapolate in a smart fashion to zero noise so that you get an indication of what this would mean for zero noise in the setting, kind of undoing the noise largely on a classical level. That's a beautiful idea. I mean, it was used by many. It's in the center of the IBM strategy, and this is a good method to, with little overhead or very little quantum overhead, to get going and reduce the setting. It's a beautiful idea. That also works. But there are also others like probabilistic error cancellation and so on. But what we wanted to know in this context is how well can this work in the ultimate limit, in worst case, asymptotically. Just to give a bit of a guideline of what we might expect in the long run, it's good to know what we can do and what we cannot do. And to do so, we formulated a kind of mathematical framework to encapsulate large classes of protocols that would include the ones mentioned, but also a couple of other ones where you have the noisy inputs. You take data and you do a largely classical post-processing, and from that you want to learn expectation values of meaningful families of observables. So this is a kind of a mathematical framework, and then this is a QTM, it's a machine learning workshop. We phrase this in the mindset of a PAC learning problem, where we ask, like, how well can this work, and what's the sample complexity? In particular, like, how many copies of the noisy states are needed to estimate the expectation values of these observables for the observers from this set of things you want to know, to precision epsilon and probability 1 minus delta, quite similarly to the PAC sign mindset I mentioned earlier. And we made this as statistical inference problem in terms of the circuit depth, the circuit width, and the depolarizing noise strength, or some similar concept along these lines. So how well can this work? Now it turns out, and that surprised us quite a bit, in that one does not need e to the power of d, but e to the power of n times d many samples. And since in the NISQ regime one expects d to be of the order log n, our results are exponentially stronger than previously known obstructions against families of quantum error mitigation. So in a way, there's already obstructions that set in at log depth of the quantum circuit. So there's the mathematician's joke that log is upper bounded by 4. And it's a pretty good joke when you think about this. Make a Mathematica plot and see what x is until you hit 4. Good luck. It's a big number. Yeah? So it's basically constant depth, and that's where, in worst case, obstructions set in. How does this work? I mean, I give you some hints into how the proof goes. So we set up a learning problem, again in the mindset of this conference, that can be solved by error mitigation, where, roughly speaking, you have a device and a classical post-processing, and you feed in either the maximally mixed state or a computational basis state, and your task is to discriminate the outputs of the noisy circuits of computational basis states from this maximally mixed state. And you make the argument that this is a weaker problem, in the sense that if you find an obstruction against this problem, you also find a rigorous and precise obstruction against the original quantum error mitigation problem. That's the least thing you need to be able to do. This discrimination already has this kind of flavor of a multi-hypothesis testing, and then we beefed up a variant of a Fano's lemma that argues that a single sample test that distinguishes these n+1 distributions, so the computation basis state and the maximally mixed one, must fail with probability at least 1 minus alpha, with a left-hand side with Kullback-Leibler divergences, and a right-hand side that gives the upper bound, and all the work comes in to bound this right-hand side that then gives the right scaling of the sampling complexity over. So most of the hard work of this paper, it has a long appendix, goes into the bounding the right-hand side here. So at least one of the co-authors of this is also here in the audience somewhere. I don't know. So meet. Good. Yeah, good. So, and then much of the hard work comes in showing that these circuits exist, that there are circuits that are so crazily scrambling in worst case, so that the bound, this Kullback-Leibler divergence, is huge. It turns out, that's kind of our magic, that it's good enough to make the purity of certain subparts small. Yeah, so they're very mixed in the 2 Renyi entropy sense, and then you have to find circuits that in worst case produce lots of Renyi 2 entropy in a very short depth. And it turns out that Clifford circuits for 2 designs are doing this in log n depth, and then you put it all together and you find that the random circuits shift the purity contribution to larger weight Pauli worlds, and then you are so scrambling, and when you put it all together, you find that at log depth, there's an obstruction. So there's strong obstructions against error mitigation already at log depth. It does not mean error mitigation does not work. It does not mean that. It just does not scale in the most drastic of senses, and it does not work for all circuits in worst case. And I'm happy to provide more intuition about this if you ask me, because there's a bit of a disclaimer here. It does not constrain quantum error correction, but it also can be seen as an invitation to think of new intermediate schemes between error correction and error mitigation, and we started doing this, and also so did others. because I think that any no-go theorem is a good invitation to think harder about new things outside the box, and our result can be seen as an invitation along these lines. In fact, the impact of non-unital noise is much more drastic than anticipated in many ways. Also, non-unital noise is funny. You can cool down systems, you can reduce the entropy, and there was this beautiful paper, not much seen, even though it's by Gottesman, on a quantum refrigerator that uses these guys as tools to do something like error correction in circuits using non-unital noise. Beautiful prescription. Anyway, what does non-unital noise do to our variational quantum circuits as we think about them in machine learning? Here's a couple of results. If you think you have a deep quantum circuit, you don't have a deep quantum circuit. Think of a random circuit with geometrically local gates in this fashion. If these dudes are non-unital, you do your deep circuit, and all you do is a little chunk at the end. Deep random circuits under uncorrected, possibly non-unital noise, get effectively truncated, so the last log n layers matter, and what you do before, you can also replace by the identity or your mother's birthday, so it will not matter for the end. So log depth is what you have, the good news, but log depth is all you have, and it will be chopped off, and that's what you have. It is what it is. Then at some point we said, great. The wonderful opening talk that we heard here by this eminent gentleman in the second row was on barren plateaus, and we stared at this problem and looked at obstructions against training through barren plateaus. He said, no, there's no barren plateaus in this setting. There's a lack of barren plateaus for local cost functions in that the cost landscape is never flat and the gradient never vanishes under non-unital noise. I thought, whoa, that's great. That was even the title of the earlier version of our paper. Until we realized, wait a minute, that's for the wrong reasons. You're not expressive enough. You have few parameters, and while you have not have barren plateaus, good news, but that might be due because you're just not expressive enough and you're dead for other reasons. But that's what it is. In fact, you can even classically simulate, on average, I've said it, on average, expectation values of any observable to additive precision with probability 1 minus delta at any depth with this label here, which means that if you are good enough with constant precision, this is efficient in any dimension. If you want 1 over poly precision, this works in, oh no, the other way around. I mean, that you can do this in any dimension with constant precision and in one dimension with 1 over poly precision, which is a pretty heavy blow. You can largely dequantize prescriptions of this type by classically simulating them. That's kind of the most general. I'm aware of dequantization results for noisy quantum circuits that challenge what you can do with quantum computers in the presence of noise. So again, log depth is all we have. That's a challenge to variational quantum machine learning approaches. So log depth is what we have, but log depth is what we have. The glass is log full, or 1 over 1 minus log full. And non-unital noise acts strikingly differently compared to depolarizing noise. There's a kind of a meta message that thinking about these oversimplified noise models can be misleading, and to capture what's going on and think of the noise models can be a crucial inside ingredient into properly understanding what's going on. Your non-unital noise can be vastly different. So 33 minutes into the talk, says my clock. I'm known for not overrunning, and I have a strong chairwoman here, so I better stick to my promises. And I will just meditate a bit at the end, and we might have time for questions, if that's okay. The good, the bad, and the ugly. So we asked, can quantum computers assist in meaningful machine learning tasks? That's a meaningful question at a workshop that asked the question whether quantum computers can assist in meaningful machine learning tasks. So that was the core question of our talk. And I have good news and bad news to offer here, which is like my 5 pence worth to this bigger picture. To start with, I have told you that there's proven separations in meaningful learning and also quantum training tasks in well-defined, mathematically well-defined machine learning models. That's great news. The field exists. I mean, Christa made the same point or a similar point, head-to-head, so to say. We need results of this type. It's good that there's proven mathematically sound separations that we have to make progress in the field. At the same time, you can say, great, but how much structure do we really need? So quantum computers are good in solving structured problems, and there's this beautiful article by Maria that also challenges this view. She argues that that the typical problems you have in machine learning are very dirty and like messy, whereas in quantum computing, we are used to very structured problems. The size of the inputs is like very large, where it's pretty small, presumably still pretty small for quantum computing. It's difficult to assess the performance and so on. So is quantum advantage even the right aim? That's a very good question. And we should meditate about this question. There was also a panel discussion earlier today at an important meeting where eminent people also discussed this, and we were like wondering. There was not a clear conclusion. There was no fist fight, but no, you laugh. I have been to a conference where I gave a talk. It was reasonably well received, and then there was a question time, and then somebody came up and literally attacked me on stage, starting a fist fight. I hope this will not happen. Well, the guy invited me later for dinner, so it was not so bad. Anyway, so there were questions asked, like, quantum computers are good at solving structured problems, and it's not so easy to make progress on the rigorous line. And there's the German saying that, should we prove quantum advantage? I think, yes. But there's a German saying that you do one thing and don't skip the other. So we should try to prove this, but that cannot be the end of the story. Like what I like to do is like to prove proof pockets. So little snippets of insights about something in the hope that when you have collected enough proof snippets along the way, then there's an image generated that gives a better understanding of what's going on the rigorous scale. But at the same time, we should not look down to heuristic approaches, non-rigorous approaches that do something. Let's not forget that like thermodynamics came up like almost 100 years after the Brits built steam engines. Yeah, I mean, there was a lot of theory coming later, that's pretty deep, called thermodynamics, but the steam engine was running and was starting the Industrial Revolution all along, so we should also take a bit of a pragmatic perspective. And I would like to see the big players that have big machines, and I think of there's people from the quantum and tech industry here, like running large-scale classical computers to really explore what's going on for some algorithms. That would be actually quite insightful, and completely heuristically explore things to big scale on classical large-scale machines. But then there's constant depth advantages. That's again good to know. Yeah, I mean it's for crackpot data, but it's constant depth over slightly longer classical circuits. That's, I think, encouraging again. That's from today. It also invites to think about outside the box and think about new avenues, new thoughts in the field, outside the beaten trails in the field. I'm also very happy to see that the field is maturing from the perspective of classical AI. There's more and more people from the classical world coming in with like strong expertise, and the days of producing like 3-qubit plots and staring at them, they're kind of over, and there's a more mature, no offense, more mature picture from the perspective of classical machine learning coming to the field, which is a very healthy development, I think. For example, that's an example for a talk that we will have on Friday on like explainable quantum AI, where we asked like, what's the role of each of the parameters in the model for classification, where we teamed up with leading experts in classical explainable machine learning that have funny examples. Like, if I have this 30 seconds. They look at classifiers that classify Russian and American tanks, which work super well. And then they're using these tools, they ask what it is that makes the tank Russian or American. It turns out it's good weather is American tank, bad weather is Russian tank. So, yeah, and never mind. And this paper is kind of interesting. It will come out next week or so, that in a way that we have technical results, but it's also like a preview in the sense of the review of papers we might write about the subject, giving a bit of perspective in the field. Then we thought of generalization bounds and challenged traditional approaches to generalization as they fail to explain the behavior of some quantum machine learning models along the lines of using mature perspectives from classical AI and bringing them into the quantum world. We thought of single-shot quantum machine learning that kind of aim at thinking about close to deterministic readings of machine learning, bringing together machine learning with notions of hypothesis testing and coming from metrology to see what we can do here to make near-deterministic machine learning. Or like thinking about inductive biases, we think of learning complexity gradually, of getting a favorable inductive bias through curriculum learning and hard example mining, where again we inherit ideas from classical machine learning and bring them into the quantum world. Again, on the bad side, log depth is all we have. Expressivity. Elias gave the wonderful talk yesterday on how expressive quantum kernels are. This is the one side. Then you can say, when can you dequantize settings? We at some point got a heart attack when we realized that many of the data re-uploading models are so structured so that you can find efficient classical sampling methods to actually evaluate expectation values at the end of the day. We got a heart attack. We thought we shot down variational machine learning overnight until we realized that the functional dependence of the control parameters and the predictions is more subtle, so there may be an advantage in the training of the model, not so much in the evaluation. But the last word in this coordinate system between expressivity, classical simulatability, and trainability, this Bermuda Triangle, has not been said, even though we heard beautiful talks even yesterday, earlier today, about this thinking. There's these beautiful approaches of algebraic settings that we also saw yesterday. We have a full classification of the Pauli-Lie algebra. Great. What are they good for? It's my invitation to things. To bring me to the last slide, because I wanted to keep my promise, maybe for now, a highly interesting, although that sounds very boring, but to me, very exciting field is to do machine learning in the brain and think about like ideas of computational learning theory and property testing to assess properties of quantum systems from the mathematical machinery of machine learning, but largely as a mathematical enterprise. There will be nice talks by Sumit, also Alex and me as a student later today on this idea of using ideas from property testing to the quantum world. And this is also practically relevant, that's my last point I'm making, in that there's tools, say, in Hamiltonian learning that I think are a very fruitful way forward here, where you realize that quantum mechanics is formulated the wrong way around. You say you have a Hamiltonian, and when you know the Hamiltonian, it can make predictions. I give talks, beginning like courses in quantum mechanics, and I show the Schrödinger equation. The students ask, yeah, great, but what is the Hamiltonian? And I say, it's given, it specifies the system. And then the students say, yeah, but look, how would I know? I mean, there's no voice speaking to me in the lab saying that's the Hamiltonian. Or if it is, then there's other issues involved. But so how can you make predictions? And in the quantum world, when you do quantum simulations, having a precise knowledge about your analog Hamiltonian is instrumental when you want to make predictions. And it turns out that this we work with Google. I'm super happy that the good old State University have something to contribute to the fabulous world of Google, where we calibrated with and for them the Sycamore chip using nice ideas of super resolution and manifold optimization, where we understood how one can robustly learn Hamiltonian in an analog device. And when you know it, you can make predictions with much more predictive power that you might not be able to do classically efficiently. But with these tools, you can learn the Hamiltonian to enormous accuracy. And this is a very healthy way of thinking about learning in the quantum realm, as I think. So, can quantum computers assist in meaningful machine learning tasks? The chairwoman looks at me sternly, so I better provide a clear message at the end of the talk. So my clear, cut, and crisp message as an answer to this question is definitely maybe. And on this note, I thank you very much for your attention. I'm looking forward to questions you might have.
Thank you. Thanks for this great talk, Jens. So are there questions? Please.
Okay, thank you for great talks. Personally, I like the idea of explainable quantum machine learning, but I suspect that's because the model is very small model. So I mean, is it easy to investigate the role each parameter in the model to see the effect in the machine learning, performance. But is there any other reason behind, the explainable quantum machine learning can be, the future direction for the...
That's a wonderful question. I will provide only a short answer, because a better answer will be given by a full talk by Jonas, who's here. Oh, here it is, in the back, who will give a full talk on Friday. So you're right. We have machinery, we have technical developments, we have 2 new ideas of explainable AI in the paper. And we also present numerical tools, but as you have suspected, they're tiny. So they're tiny and they're not of the scale as you would know them from the classical world. They're kind of, in a way, ridiculous compared to the classical world. We just did this to showcase what ways of thinking would be healthy in that setting. But again, the format that we advocate is like that of a preview, that we really carefully go through ideas that might work, but we don't explore all of them. So this is seen as an invitation to people like you to carefully look at this and do something better that we can, because we are not claiming to have a full picture. But there's some subtleties that are different quantumly than classically. For example, that you cannot just look at the system and get the state in one shot and learn what's in intermediate steps available, because that's a quantum state that you will need to learn in order to make predictions. So there's some interesting subtleties. So take this as an advertisement for the talk.
Yeah. Okay, well, one question.
Thank you very much for your nice talk. I'm just wondering why noise cannot be tolerated to benefit generalization, because from the classical AI/ML world which I'm coming from, especially in large language models, large vision models, noise is a blessing, is not a curse. Why in actually quantum models quantum computing community is that much actually concerned about drasticality of the noise?
Yeah, okay, there's many things to be said. Actually, I give the quantum course, as I said, and I tell my students that I never lie, but sometimes I do sweep stuff under the carpet, right? So this is, here I did say it, but maybe you didn't hear it, and I was mildly swiping this under the carpet. And the way we look at it is a very sound and important setting in average case. We can take a quantum circuit and we make an average case statement on how impactful the noise is. But that's in average, it's not in worst case. And you can back engineer some settings where the noise is a blessing, even in the quantum world. I suspect that this is much less good news than you would hope this to be. I think in the classical world it's much better to have, whereas, and we even have an example, also I didn't mention this with Yunyu, where the paper where noise actually provably helps, but I suspect it's not so helpful as in the classical world. But there's some settings where it can help, and you can really cool down parts and use these low entropy guys as resources in error correction like settings that even help to go in the long run. So we know of these sweet spots, even in the quantum world. I'm happy to say more in the coffee break, but don't put all your impetus in this. It's a blessing with some downsides as well. But I'm happy to, I have something to say. We discussed this.
Okay, unfortunately we need, no, it's too late.
Okay, good. Thanks for the interest. We discussed
Sorry, let's thank Jens again.
Wonderful.